Hello students, this is Professor Chalai, and in this video we're going to look at reaction stoichiometry. As always, you can follow along with our chapter 4 workbook. By the end of this video, you should be able to obtain stoichiometric ratios from chemical equations and also use those stoichiometric ratios to perform stoichiometric calculations. So what is stoichiometry and what is the stoichiometric ratio that we keep talking about? Well, the stoichiometric ratio is simply the ratios of the different molecules that you see in a balanced chemical equation. So stoichiometric ratio or stoichiometric factor are the ratios of the different molecules in a balanced, and that's key there, it should be a balanced chemical equation. And so this is why we spend so much of our past couple of lectures talking about how to balance chemical equations. So let's look at the equation as an example, the equation in question 19, which is already balanced for us. In here, we see that in this, here for every one molecule of propane, it will react with 5 molecules of oxygen to produce 3 molecules of carbon dioxide and 4 molecules of water. Those numbers, so 1 for the propane, 5 for the oxygen, 3 for the carbon dioxide, and 4 for the water, those are the stoichiometric factors. So if you knew the number of moles of any one of these, for example, if you knew the number of moles of propane, you can easily find the number of moles of oxygen or the number of moles of carbon dioxide or the number of moles of water using the ratios. The number of oxygen will be 5 times as much as the number of moles of propane. The number of moles of carbon dioxide will be that much more, 3 times as much as the moles of propane, and so on and so forth. So those numbers in a balanced chemical equation helps in stoichiometric calculations. And this is why we have spent so much time balancing chemical equations. Because of that, once you're able to figure out the number of moles of one molecule, let's call it molecule A, you can use the stoichiometric ratio to relate to moles of any other molecule in the equation. Let's call it molecule B. And then we've learned from number of moles, we could go to mass using molar mass, and then volume using density. Or from moles, we can go to volume using molarity. Or from moles, we could even go to number of molecules using Avogadro's number. There are many different directions we can go with once we figure out the number of moles. Similarly, if you start with the volume or the mass or the concentration and volume or the number of particles, you can calculate number of moles and perform your stoichiometric calculation that way. This is one of the reasons why I've mentioned earlier in this course that if you're able to find a number of moles of something, you'll go a very long way in trying to figure out any specific calculation. So let's see this in practice. Let's look at number 19. In this question, it says how many carbon dioxide molecules, so this is our question, are produced when 0.75 moles of propane is combusted according to this equation. So we're starting with 0.75 moles of propane. I'll just write C38H8. And we need to figure out how many molecules of carbon dioxide that we have. Before we can do that, we need to translate our number of moles of propane to our number of moles of carbon dioxide. And we see that the ratio is for every 1 mole of propane, we're going to have 3 moles of carbon dioxide. So let's write that. And since we need to cancel out moles of propane, we'll put that in a denominator. For every 1 mole of propane, C3H8, we have 3 moles of carbon dioxide. So that cancels out nicely. So now that we've converted our moles of propane to our moles of carbon dioxide using our stoichiometric ratio, all that we are left to do is convert that to number of molecules. And we can convert from moles to number of molecules, if you don't remember, using Avogadro's number. So let's do that. Avogadro's number is 6.022 by 10 to the 23 molecules per there we go, molecules per mole. So moles cancel out. And what we end up with is, if we plug all of these numbers into our calculator, I think we end up with 1.4 by 10 to the 24 molecules of CO2. Like I mentioned, as long as you could figure out number of moles of any of the components, you can use mole ratios to figure out other components. So let's see if you can try number 20 on your own. Pause the video, balance the equation, and then solve part B as well. Unpause the video, and I'll go over it with you. Okay, so in number 20, let's start with the balanced chemical equation. It says that we start with aqueous silver carbonate. Silver, we know, has a charge of +1. Carbonate has a charge of 2 minus. So silver carbonate should be Ag2CO3, and they tell us it's aqueous. AQ. Okay. Then we have aqueous hydrochloric acid, which hydrochloric acid has formula HCl, so it's HCl aqueous. And this goes to form solid silver chloride. Again, silver has charge of +1, chloride has charge of -1, so we form silver chloride solid and aqueous carbonic acid. Carbonic acid, if you remember, comes from carbonate, CO3, 2 minus. So we need 2 H pluses to balance that, H2CO3 aqueous. Okay, let's balance this equation. We see that there are 2 silvers on the left, but only 1 on the right, so I'll make this whole thing a 2. This gives us 2 chlorides on the right, but only 1 on the left, so I'll make that a 2. That gives us 2 H pluses on the left, 2 H pluses on the right. That seems okay. And then we have 1 carbonate, CO3, 2 minus on the left. We have 1 carbonate on the right. So everything should now be balanced. Okay, now that we have a balanced chemical equation, we can perform stoichiometric calculations. So let's look at what they're asking for. They're asking for the mass of hydrochloric acid in grams. And what we have is, what we've reacted with is 10 grams of silver carbonate. So we started with 10 grams of silver carbonate that completely reacts to form, They wanted to figure out what mass of hydrochloric acid reacts with that silver carbonate. So let's figure it out. The first step is to convert the number of moles of what we're starting with, which is silver carbonate. So we have 10.00 grams of silver carbonate. And we need to find number of moles. We find number of moles by using the molar mass. So the molar mass of silver, Ag2CO3 carbonate, is going to be 2 times the molar mass of silver, 107.87, plus 1 times the molar mass of carbon, 12.01, plus 3 times the mass of oxygen, which is 16.00, all that grams per mole, which gives us a molar mass of 275.75 grams per mole. So to convert this into number of moles, we have 275.75 grams of silver carbonate to moles of silver carbonate. I keep writing the molecule all over again just to make sure that we keep track of which molecule we're working with at any one time. So grams of silver carbonate cancels out. Now that we have moles of silver carbonate, we can convert that to moles of hydrochloric acid using our mole ratio. So we know that in this balanced equation, for every 1 mole of silver carbonate, we have 2 moles of hydrochloric acid. So 1 mole silver carbonate reacts with 2 moles of hydrochloric acid, so that moles of silver carbonate can cancel out nicely. All right, now that we have moles of hydrochloric acid, they're asking us for mass of hydrochloric acid in grams. We can figure that out by converting from moles to mass using the molar mass. So the molar mass of HCl would be the molar mass of hydrogen plus the molar mass of chlorine. So that adds up to 36.46 grams per mole. So we multiply by 36.46 grams of HCl per mole of HCl. Again, I'm just keeping the HCl there to make sure we know what we're working with. So moles of HCl would cancel out, and we're left with grams of HCl as our answer. And so this becomes, if we plug all of this into our calculator, 110 divided by 275.75 multiplied by 2 multiplied by 36.46 gives us 2.644 grams of HCl, which is what the question was asking us for. So let's look at this again. We take the mass of silver carbonate, convert it to moles of silver carbonate. Then we take the moles of silver carbonate, convert it to moles of HCl using the Molar ratios or the stoichiometric ratios, and then convert that number of moles into mass using the molar mass again, but this time of HCl, to give us our answer. I have 4 sig figs in our answer because we started with 4 sig figs, and the mole ratios are exact. There's going to be exactly 2 moles of HCl that react with 1 mole of silver carbonate. All right, questions 21, 22, and 23 are all very similar, so I'd like you to pause the video here and try to work those out by yourselves. When you unpause, I'll go over all 3 of those. Okay, let's look at number 21. They already have the balanced equation for us, so this makes our life easier. They tell us that the plant consumes 37.8 grams of carbon dioxide, and then there's enough water to react with all of this carbon dioxide, so we don't need to worry about the water. And all of this goes to form hang on. All this goes to form glucose. There we go. I was looking for the word. So how much glucose in grams, let's use a different color so that we can highlight that. So how much of the glucose in grams do we form by using up 37.8 grams of carbon dioxide? Well, let's figure it out. So we start with 37.8 grams of CO2, and because we need to, this is a stoichiometric calculation, we need to first convert to number of moles. So the molar mass of CO2 is the molar mass of carbon plus 2 times the molar mass of oxygen, which comes out to be 44.01 grams per mole. So we can use that. And let me just move this down a little. There we go. So that I can make some space. So 44.01 grams of CO2 per mole of CO2. So we've now converted to moles of CO2. Now we use the mole ratio. We're going to use the mole ratio to convert from moles of CO2 to moles of glucose in this equation. So in this equation, 6 moles of CO2 goes to form 1 mole of glucose. So 6 mole of CO2 forms 1 mole of glucose. I'm just going to put GLU for glucose. And so moles of CO2 cancel out. And now we need to convert moles of glucose into mass of glucose using the molar mass. So let's calculate the molar mass of glucose. So molar mass of glucose is going to be, it's C6, so the molar mass of carbon times 6 plus H12, so it's molar mass of hydrogen times 12 plus and it's O6, so that's the molar mass of oxygen times 6 grams per mole. So that becomes 180.18 grams per mole. Let me know if my calculations are wrong. Sometimes I can maybe punch in incorrect numbers. Okay, so this gives us 180.18 grams of glucose over moles of glucose. So moles of glucose there cancel out. So for our answer, what we're left with is grams of glucose, which is what we're looking for. So if we punch all of these numbers into our calculator, we get 25.8 grams of glucose to 3 sig figs, because that's what we started with here. Okay, let's take a look at number 22 now. Number 22, similar equation. they've already balanced it for us. And again, we're starting with grams of milk of magnesia, which is magnesium hydroxide, and they're asking us for the mass of sodium hydroxide that it gets used up with it. So let's figure that out. We start with 16 grams of MgOH2. We multiply that, divide that, sorry, by the molar mass of MgOH2, which I'm not going to do the calculation, but it's 58.33 grams per mole. So it's 58.33 grams of magnesium hydroxide per mole of magnesium hydroxide. Now that we know the moles of magnesium hydroxide, we can convert to moles of NaOH. So in this equation, for every 1 mole of magnesium hydroxide, we get 2 moles of NaOH. So 1 mole of magnesium hydroxide for every 2 moles of NaOH. So that leaves us with moles of NaOH. And then finally, so let's separate that. Finally, we can convert to mass of NaOH by using the molar mass of NaOH, which is, if you do the calculation, 40.00 grams per mole. So let's use that. So 40.00, whoops, that's not 40, that's 4. 40.00 grams of NaOH per mole of NaOH. So then we're left with mass of NaOH, and that gives us, if we plug all of these numbers into our calculator, 22 grams of NaOH as our answer. To 2 sig figs, because we started with 2 sig figs. And then finally, let's look at the last one. I realize all of these are going from mass of one thing to a mass of another, but as this chart shows, we can start with not just mass, but any of these quantities and perform the same set of calculations as long as we convert it to number of moles first. So that's something to be aware of. These are all masses, but you can use any sort of starting quantity. So here they're asking us for the mass of oxygen gas that is consumed when we burn 702 grams of octane, and we already have the balance equation, so that's all good. So let's do it. We have 702 grams of octane. I'm just going to write OCT. We need to convert that to number of moles. So the molar mass of octane is 12.01 times 8 and 1.01 times 18 grams per mole, which is, let's see, 114.26 grams per mole. So let's divide 114.26 grams of octane per mole of octane. Okay, now we use the mole ratios. In this example, we have 2 moles of octane, so 2 moles of octane reacts with 25 moles of oxygen. And then finally, we convert to mass of oxygen by using the molar mass of oxygen, which is just 2 times 16.00 grams per mole, or 32.00 grams per mole. So we're going to multiply by 32.00 grams of oxygen per mole of oxygen. So moles of oxygen cancel out, and we're left with grams for oxygen as our answer. So if we plug all of these into our calculator, I get 2,460 grams to 3 sig figs, because we started with 3 sig figs over here. So this is the crux of stoichiometric calculations. It all depends on the balanced chemical equation that you start with. So knowing how to balance chemical equations is a key first step. Once you have that, and you can do all of the various mole conversions, so convert any of the quantity first to moles, use the mole ratio to convert the moles of one thing to the moles of a second thing, a substance in a chemical equation, and then convert the mole of that second substance into any of the other properties that we've learned about. That will bring us to the end of this video to going over stoichiometry. But you can bet going forward in this course, stoichiometric calculations are going to come up a lot, as will balancing chemical equations, because those are some key steps in figuring out various quantities in chemistry, especially general chemistry. So there are more practice questions towards the end of the chapter as usual. In the next video, we're going to go on to talking about reaction yields, including limiting reactant and theoretical yield. I'll see you then. Bye.